Good morning, everyone. Can you hear me and can you see my slides?
Yes, we can hear you
Yes.
perfectly well. Thank you, Adolfo.
Okay, thank you for being here. Thank you for the invitation. Today, I will be sharing a practical approach to soil monitoring, focusing on uh, indicators and the development of a synthetic index to support interpretation and communication. Well, as you have said, I have a background in biology and agroecology, and I'm currently finishing my PhD in biodiversity and conservation program at the University of La Laguna. I work in the soil health laboratory, where we designed and evaluate ecological restoration intervention, especially in drylands and areas affected by land degradation. My research focuses on using soil monitoring indicators not only to assess ecosystem function, but also to support decision-making in restoration planning and land management. Well, in this session, I will go over the main soil indicator I work with. What they tell us, how we measure them, and how we can bring them together through an ad hoc soil quality index. I'm sure some of you are more experienced than I am with certain parameters, and that's totally fine. But the idea is to do a quick but structured review, and at the end, I will show you a case study from Lanzarote, where we applied this in the field, and we will wrap up with a short discussion. Soil indicators are measurable variables that reflects the state or function of soil. We use them to track degradation, monitor the impact of restoration actions, or inform land management decision. Ideally, good indicators are quantitative, repeatable, and interpretable across space and time. When assessing soil health or degradation, we usually classify soil properties into three main groups: physical properties, like texture or bulk density, which influence water rotation, porosity, and structure; chemical properties, like pH, salinity; nutrients or iron concentration, key for fertility and reactivity; and my favorite ones, biochemical properties, which reflect biological activity in the soil. Things like microbial biomass, respiration, enzyme activity. Each group provides different but complementary information, and together they give us a more complete picture of soil functioning. These are the main physical indicators, the physical indicators we work with in our soil monitoring programs. These indicators help us understand the soil structure, porosity, and water holding capacity, all essential for plant growth and ecosystem functioning. Uh, these are the chemical indicators we usually assess. First, we have general soil chemistry with parameters like electrical conductivity, pH, exchangeable sodium percentage, and the main exchangeable cations: sodium, potassium, calcium, magnesium. Then we look at nutrients, including total nitrogen, available phosphorus, and a wide set of soluble ions and micronutrients like copper, iron, zinc. And finally, we assess different forms of carbon: total carbon, organic carbon, labile carbon, and inorganic carbon like calcium carbonate. And lastly, we assess the biochemical indicators. We start with microbial biomass carbon, which gives us an idea of the size of the active microbial pool. Then we have basal respiration, which reflects microbial activity. And from that, we can calculate the metabolic quotient, or QCO2, a stress indicator that tells us how efficiently microbes are using carbon. We also assess enzyme activities, beta-glucosidase for carbon cycling, urease for nitrogen, and phosphatase for phosphorus. These indicators provide insights into the soil biological functioning and nutrient cycling capacity. Often the most sensitive early signal of change. That's why are my favorites. We begin with two key physical indicators, bulk density and aggregate stability. Bulk density is the mass of dry soil per unit volume. It tells us how compact the soil is. High bulk density usually means less pore space, more resistant to root growth, and poorer water infiltration. To measure it, we take intact soil cores, dry them in an oven at 105 Celsius degree for 24 hours, and then weigh them. Then we have aggregate stability, which show how well soil particles remain grouped when exposed to water. It's important for soil erosion, infiltration, and also for root penetration. Another indicators are these three. Those indicators help us understand how much water the soil can hold and provide to plants. First, field capacity is the amount of water soil holds after gravity drainage. It is the maximum water available to plants after rain or irrigation. Permanent wilting point is when soil is so dry that plants can't take up water anymore. Then available water is the difference between field capacity and wilting point. It's actually the water plants can use. We measure field capacity and wilting point in the lab using Richter plates, applying suction pressure. Those indicators are especially important in drylands where water is limited. One of the most important is soil texture. This property tells us how much sand, silt, and clay the soil contains. We measure this using a hydrometer method based on how fast particles settle in water. We also check coarse fraction, particles larger than 2 millimeters, which affect water rotation and root penetration. The texture ratio is not a standard indicator or common property, but we use it as sand plus silt over clay. It helps us compare soils. Lower values often mean finer or more compact soils. Texture, we are talking about texture, influence almost in everything. Water holding, aeration, nutrient retention, and even erosion risk. Let's continue with two basic but important indicators, electrical conductivity and pH. Electrical conductivity gives us an idea of how salty the soil is. The higher electrical conductivity, the more salts are present. Too much salt can make it hard for plants to absorb water or even germinate. We measure electrical conductivity in the saturated past extract. That is here. We're using conductivity method. Then we have soil pH. which tell us how acidic or alkaline the soil is. pH affects how nutrients behave, how microbes work, and how roots grow. Just like electrical conductivity, we measure it in the saturate past using a pH meter. Now, we move to a group of indicators related to cation exchange and sodicity. First, the exchangeable cations, sodium, potassium, calcium, and magnesium, are the main positively charged ion attached to the soil exchange complex. We have here a representation of this exchange complex. Those exchangeable cations, are essential for soil structure and nutrient balance. We extract them using a standard ammonium acetate method, which replaces them from the soil surface. Then we have some other metrics like sodium absorption ratio. The sodium absorption ratio compares sodium to calcium and magnesium, and help us assess the risk of sodium-related degradation. And with this parameter, we can indirectly calculate the exchangeable sodium percentage. This exchangeable sodium percentage tells us what proportion of the total exchangeable cation is sodium. High exchangeable sodium percentage values are typical of sodic soils, which often suffer from poor structure and water infiltration issues. In our case, we calculate, as I said, sodium percentage, exchangeable sodium percentage from SAR, following the United States Salinity Lab guidelines. Let's look now at some important chemical indicators. First, we measure total nitrogen by dry combustion with gas detection. In this instrument, we call it LECO, it's the LECO brand. Nitrogen is a macronutrient, it's a very important nutrient. Then the available phosphorus, we measure it with the Olsen method. And potassium, nitrogen and phosphorus and potassium are main nutrients. The potassium, we measure it with all the soluble ions in the soil solution. And then we have the micronutrients, copper, iron, zinc, and manganese. They are needed in a small amount, but essential for plant health and microbial activity. And the soluble ions measured in the saturated paste strate, sodium, potassium, calcium, magnesium, fluoride, chloride, nitrate, sulfate, and bicarbonate. This ion gives us a picture of salinity and nutrients in the soil solution. Carbon, the star element of the soil. First, we measure total carbon also by dry combustion in the same instrument. And then we distinguish the soil organic carbon, which is the part associated with organic matter. We use the chromic acid wet oxidation method to determine it. Then we assess labile carbon. It's also an organic carbon, but it's the most active and easily degradable fraction. It reacts fast and gives us information into the microbial activity. And finally, we look at calcium carbonate, the main form of inorganic carbon in many dryland soils. We measure it with a calcimeter by reacting the sample with hydrochloric acid and measure the amount of carbon dioxide released. Now we move to the biochemical properties, which are my personal favorite ones. They give us a direct window into soil biological activity. First, we measure microbial biomass carbon. It is the living part of the soil organic matter, the microbial engine that drive nutrient cycle. We use the fumigation extraction method to estimate it. Then we look to basal soil respiration, which tell us how much carbon dioxide the soil releases under controlled conditions. It reflects microbial metabolism and gives us a sense of overall soil biological activity. Continue. Let's look at soil enzyme activities, which reflect microbial function and nutrient cycling. First, beta-glucosidase. It catalyzes the hydrolysis of beta-glucosidic bonds, like converting cellulose into glucose. It is a sensitive indicator of carbon cycling, and we measure it using salicylium as a substrate, following the Strebel and Muller method. Then urease, which breaks down urea into ammonium, important for understanding nitrogen cycling. And finally, phosphatase, which help release phosphorus from organic compounds, giving insights into phosphorus viability. These enzymes are responsive and informative, great tool for tracking soil biological shift. Okay, so that was our tour through the main soil monitoring indicators I use. And now we shift and we talk about how to make sense of all that information. The soil quality index helps us to synthesize diverse indicators into a single number, usually on a 0 to 1 scale. It makes easier to interpret and communicate soil health results, both to technical teams and to land managers or decision makers. And very important, this is not a fixed or universal index. The soil quality index is an ad hoc, meaning we adapt it to each project, each landscape, each objective. Later, we could open a discussion about how to choose the right scoring function for each parameter, depending on your context. Building a soil quality index involves some steps. First, we select the indicators based on your objective and the context of the project, because not all indicators are always needed. Second, we need to standardize the results. Each indicator has different units and scales, so we transform them into a common scoring system from 0 to 1. This is where scoring functions come in. Some variables are better with higher, and we use this scoring function. For example, soil organic carbon, microbial activity. Some, when lower, for example, bulk density or electrical conductivity. Another have an optimum range. Finally, we aggregate the scores into a single value. This can be done by averaging or sometimes using weighted scores if some indicators are more relevant. But how we know that some indicators are more relevant? We have some tools. After measuring all indicators, we need to narrow down the list. We filtered out redundant or irrelevant variables using some of these tools. First, we applied the predictive power score, which is helpful because it's asymmetric, so we can detect unidirectional relationship. Then we use analysis of the variance to remove variables without significant treatment effect. Treatment or zone or variables that do not have differences in your experimental design. Then principal component analysis help us to reduce dimensionality. We keep components with enough explanatory power and select indicators with strong loadings and low collinearity. And finally, at the end, also with the principal component analysis, we use the loadings of this analysis as weights to compute the final soil quality index, to measure the importance of every indicator in the result of soil quality index. Let's see, for example, the first tool, the predictive power score, the predictive power score matrix we use to start these processes. It looks like this. What is nice about the predictive power score is that it's asymmetric, as I said, and it tells us how much a variable A predicts variable B, but not necessarily the other way around. I mean, for example, slug, soil level carbon, predicts total nitrogen with this score, 0.59. But nitrogen predict slug, soil level carbon, with less score. So we can keep slug if we want, and we can remove nitrogen because the information that nitrogen gives us, slug also give it to us. It's an example of a tool that we can use to go to the minimum data set to reduce the number of indicators we need for the soil quality index. Okay, this is to resume the processes. For soil quality index development, we have the soil properties. We choose the scoring function. For example, bulk density, less is better. It's easy to understand. Some of these properties are not so easy to choose a scoring function. It depends on your context. To eliminate redundant information, we use correlation matrix and the predictive power scoring. To select relevant information, ANOVA, and also principal component analysis. And then to obtain the weighting factor, we use also the principal component analysis. We multiply the weighting factor and the score, and the summatory give us the soil quality index. Let's see it in an example, a study case. This is the map of the case study on Lanzarote, Canary Islands. This area well, Canary Islands is this archipelago close to the Northwest African coast, and we belong to Spain. And in Lanzarote, in this mountains, we have this place we call Altos de Famara, around 600 meters above the sea level. The place look like this. You see the badlands, and not a lot of vegetation, and degradation processes are in progress. What are the climatic conditions of this place? Constant winds, high solar radiation, and very low precipitation. For example, from summer 23 to summer 24, the rain was 110 millimeters, and the evapotranspiration, the potential evapotranspiration was 1,000 millimeters. So it was one order of magnitude bigger than rain. It means that this year was an arid condition, very arid. The soil degradation in the three blocks that we were talking at the beginning. Physical soil degradation, we have low infiltration, loss of soil structure, and erosion. Chemical degradation, low carbon, soil organic carbon, and low nutrient contact. And biological degradation, because we have absence of vegetation cover and low microbial activity. To start, we classified the study area into distinct ecological zones based on vegetation cover, vegetation type, exotic plantations like Pinus halepensis, and Acacia cyclops, and the degree of degradation. Okay, so we have this soil sequence from badland that have the highest degradation, plain with no permanent vegetation and some degradation sinks, then two exotic plantations, and three scenarios with native vegetation, permanent vegetation, one of them with lithic mulching, another one that are plants that survive or resist the erosion and retain the soil. So they are like remnant vegetation, and the vegetation in the cliff, the areas of soil with vegetation in the cliff that are protected from herbivory. And from all kind of anthropic pressure. You can see the badlands, very, very tall. Plains, pinus and acacias, lithic mulch, remnant vegetation, and herbivory exclusion. In these scenarios, we have here detailed pictures of the lithic basaltic lapilli. This almost the same. The plains are like mulched places, but without mulch, so they don't have good water retention, and they have no permanent vegetation. Baldan, as we said, very clay. Here we can see the remnant vegetation effect on soil, how this core of plants, of very biodiversity core of plants, keeps the soil. So they have very different soil to the rest of the soil around them. So they have this area, and pinus and acacias, these two plantations, around 60 years from their plantation, and the cleft. to access to the soil of the cliff, we have to climb. We pay climbers to take the samples. And this picture is how the area it's classified. Okay, look to the colors because now we calculate the soil quality index and we are going to see how the soil quality index reflects the diversity of soils we have in this area. We take a lot of samples, taking the samples consisting to take soil from 0 to 25 centimeters, and we transport it to the laboratory and make this pool of soil parameters that we have talked about. Here we have some pictures of the sampling experience, the samples, and the results. This is the soil quality index results. And we see how the quality grows in the soil sequence, how we go from lowest or more degraded soils to more conserved soils, and how the soil quality index, it's a good a good proxy, a good tool to express in a simple way how is the quality of those soils. Then we can, for example, study the soil communities. We did it with mesofauna, with macrofauna, but represented only with Coleoptera, also with microorganisms, with fungi and bacteria. And we found that the soil quality index is positively correlated with the richness of those 4 and different soil communities, soil biological communities. That gives us the opportunity to see how soil quality index can be useful to inform and predict a lot of the soil state, how soil is. Okay, and with this, I finished with my presentation. Thank you. And if you have any question, or you want to talk about the scoring function or how to apply it to your scenario, I'm open to those questions. Thank you.
Thank you very much, Adolfo, for your excellent presentation. It was a practical and interesting overview of soil monitoring indicators and the soil quality index, which will help us better understand for the complexity of soil health assessment. And as you mentioned, now it's time for questions and comments. So please, once again, if you would like to ask something, feel free to raise your hand or interrupt us if you prefer, or type the test in the chat.